Hello, Dan Olds here on behalf of Hyperion Research and insideHPC, and I'm here with Simon Burbidge, and we're going to talk about his storied career in HPC and what he sees for the future. How are you today, Simon?
I'm fine, thanks, Dan. How are you?
I'm doing okay. I'm fine. So, how did you get involved with HPC in the first place?
Well, I think I've been involved in HPC more or less forever. When I was at school, we started out and there was a computer hobby class that you could do when we were teenagers at the local technical college, and there was an ICL computer there, and we went over with our punch cards and did computing.
Starting with the cardboard.
As kids, yeah. And I kind of went on to do a degree in computer science and chemistry, and then went into HPC straight from there at a Central University Computer Centre at the University of London.
What were you doing there?
I started out in the QA team, looking after system integration and system building. Carried on doing that for a few years, gaining more and more expertise on the CDC computers of that time and IBM mainframes, and moving on to Cray systems.
Okay. What are you doing now?
So I'm now working at the University of Bristol, which is in the west of England. I'm the Director of Advanced Computing at the university and looking after the HPC computer services to the university.
Oh, very nice. Very nice. What have been some of the biggest changes that you've seen over the years in HPC?
So I guess the biggest change was the migration from special supercomputers like the original Cray 1s and the Cray 2.
Sort of the hand-built supercomputers?
The hand-built ones, purpose-built. And the others that were like that, like the Convexes and the MassPars and things like that. Changing to use commodity microprocessors like the Intel processors, like the IBM Power chips, like the Spark chips. And so beginning the building of clusters rather than purpose-built supercomputers.
So moving from supercomputers to dedicated Unix systems, which is kind of where my career started, but then moving into the land of entirely commodity for the most part. Yeah,
very much commodity at the moment. But I think the scalability of that is now becoming a challenge, and we're seeing some of the architecture moving back to more dedicated and specific hardware for HPC, the advancement in the interconnects, but also in the packaging, like the cooling and the density and things like that that are needed if you really want to scale up to through the exascale to pettascale and beyond.
Yes, very true. There are a lot of challenges inherent in that, and a lot of people seem to think that it's all on the software side, but it's on the hardware side as well.
It is, but I think it's always been on the software side.
Oh yeah, predominantly.
You had to vectorize your Cray code to get the most out of it, and people would spend a lot of time.
Very true.
Maybe that's something we've lost some of that on the way with standard processors and very reliable compilers. People just assume if their code runs, it's running well, but that's not the case anymore. And so as you get more and more parallel, that's less and less the case. So more work, more software engineering is required to make the most of the current computers.
So you see hardware becoming more differentiated for HPC than it has been the last few years?
I think so, yes.
Okay, and that would probably take in more exotic accelerators, FPGAs, things like that?
Certainly does, yes. Anything that we as scientists can take to make something go faster, we'll have a go at that. So anything that comes along, even if it is something that was invented to go into a teenage boy's bedroom to make the dynamics of the computer games look better, we use that. That's been very successful. Let's see what's coming up from the vendors along similar or different lines and how we can use those.
Is there anything that particularly excites you? Well, what's coming down the road in HPC, or concerns you, or both?
I think there's two things that excite me at the moment in the technology. The first is the advent of newer processors, in particular the ARM designed processors. Now, we are involved in a lot of that work at Bristol, so it's of particular interest to me and the researchers here. But I think it does genuinely give some more competition to a classic Intel-based architecture.
Especially with that just being announced, topping the top 500 list
Top
at
500,
215
yes.
petaflops. That's a big, big deal for ARM.
That's a big deal. And if you look at the numbers on that top 500 score, there's great improvements in the efficiency and the performance of those machines. So as they scale up, they will do better than one with a classic architecture.
Also, interestingly enough, that's an all CPU machine.
Exactly. So maybe we don't need to have accelerators. If you redesign your CPUs to have the capability of doing the amount of maths that you need and have, for example, the memory bandwidth to get those vectors and matrices in and out of the memory, then why wouldn't they be better than a GPU? They're both made of silicon.
That's true.
Both made with the same design. It's just how you organize that design on the chip.
But you know, one of the systems that caught my eye was NVIDIA's Selene system that most definitely is GPU based. It is very highly efficient on a watts per flop basis.
Yes, yeah.
And that was interesting to me, given the propensity of GPUs to suck down an awful lot of electricity.
Well, they do, but any processor doing a lot of work is going to use a lot of power. It's kind of more how efficiently it does that.
Exactly.
The performance comes through. And I think previously, GPU-based accelerated systems have had GPUs and CPUs, and the CPUs have really been a bit of an overhead on those systems.
Yeah.
So if you take out as much of the CPU component and host the GPUs in a much more optimized cut-down environment, then you can get those GPUs doing what they're good at and throw away the CPUs that you don't need in those systems.
And that's also, I think, a unique opportunity for ARM because, as you say, the CPUs on those systems are basically traffic cops. And they don't do, some of these big systems, I think, the Summit system at Oak Ridge, more than 90% of the performance is coming from the GPUs.
And the GPUs that have the beef.
Yes, yes. Is there anything that has you concerned about the future in HPC?
I don't know, it concerns me. I think one of the things we have to watch out for is energy consumption. Total energy consumption and power efficiency. I mean, we will have a responsibility to keep our planet safe and the environment, and reducing the amount of energy we use to do computing, it would be a really good thing. So if we can look at the efficiency, which is kind of the nature of HPC, it's always down to efficiency, speed, and performance. It's that same kind of parallel equations, simultaneous equations that have been there for all those years. So it's just a matter of making one of those equations a bit more important than the other one and say, well, actually the electricity is expensive and gee, it's not good for the environment. So let's tweak the equations a bit so we get more computing for less power.
Absolutely. And, you know, that's the way advances in computing have come, typically from HPC first.
I think so, yeah. It's the leading edge. And some of the stuff we do never gets to see the light of day, but other stuff is good. You know, things like using vectors to do faster calculations more effectively, that came from HPC in the real beginning. Sure.
Well, thank you, Simon. This has been great. Really appreciate your time. Have a good rest of your day.
You too.
Thank you very much. And this has been another chat sponsored by Hyperion Research and InsideHPC. Thank you all for watching and listening.